Welcome to the first ever Passive House Cup. Passive House Canada, the Instituto Latinoamericano Passive House, and the Passive House Network are coming together to celebrate Passive House across our whole continent. So thank you all for being here, no matter where you are located and where you are joining from.
Hi, everyone. I'm Jessica from Passivhaus Canada. The first set of projects that we'll be showcasing today in Game 1 are the small projects, beginning with Cedar Place from Canada, presented by Fletcher Noonan of Montaigne Architecture.
I'm an owner at Montaigne Architecture Works. We have a sibling construction company called Bobsled Construction, and the majority of our high performance work is both designed and built by us. So we really feel that the synergies, the closeness, the shorthand communication, all of these things are vital in getting projects like this done. They're not easy. You may or may not know, Winnipeg, has some extreme temperatures. There's seasonal temperature swings of in the neighborhood of 80 degrees Celsius. So we're going from regularly minus 40 at the depths of winter, and plus 40 is not an uncommon high in the summer. And coupled with strong winds and exposure and all of these things, it's not an easy place to live or to build. In our location, we're in the Red River Valley. Our soil conditions are also quite challenging. I'll touch on that in a slide coming up in a moment. I just have the next slide, please. We'll go to that, I guess, quickly. So this starts to describe our building form factor. As we all know, in passive house design is extremely important. This project gave us an opportunity to almost experiment with the notion of a cube. A lot of the plan and the section is, there is a very visible kind of 9-square grid embedded in it. It's almost like a truncated Rubik's Cube in some ways. Because of the challenges here with our soils, the expansive clay soils, almost any building, regardless of size, requires a deep foundation. So 30-foot typical pile depths, and the connection to any sort of main floor structure or basement becomes a real challenge for heat loss in passive house construction. So in this case, our approach was to elevate the cube essentially on a perimeter grade beam that is decoupled from the passive house envelope. So that's decoupling the crawl space and service area. The garage, there's an attached garage that is essentially decoupled with an unconditioned space, kind of as the primary owner entrance. The visitor entrance is to the front street. This neighborhood is unique in that it's a pedestrian walkways on the front only. So it's the car access, vehicular access, which is very important in a city like Winnipeg, is only from the back lane. So it's unique locally in that sense, and provided some interesting opportunities. Next slide. As you can see, some of the systems here. So what you can see is the wall system. It's a 2x6, fairly typically wood framed wall, plywood sheathing on the outside of the 2x6 structural wall, and a open web wood joist attached to that structural wall. That open web wood joist has about 18 to 20 inches of dense packed cellulose and the structural wall is also insulated. So you get our performance there. The floor trusses are supported on kind of this perimeter grade beam that just acts as a curb. The floor trusses are about 30 inches deep, and again, dense packed cellulose throughout. And then you can see here, there's a bit of a service cavity above. So the sheathing layer on top of the open web wood joist is the sheathing is our air and vapor barrier. So again, it's plywood, and it's been all the joints have been taped and sealed. And there's a service cavity above that for running our ductwork and any electrical. If you move to the next slide, and this is a construction progress photo. It shows you what we just talked about there. Another element in this is large window and door openings. So we're lucky enough that this particular street orientation gives us a lot of southern exposure. So we were able to tune our window openings and allow enough solar radiation to enter the building to meet our energy targets, obviously. So in this case, because we want our windows positioned in the middle of our insulation layer, we had to devise a way of cantilevering out these large, heavy windows into that non-structural truss space. So that's a really good collaboration between the build team of Bobsled, Montane Architecture Works, and we also had Airtight Engineering, who's from the next province over in Saskatchewan, provide support in our passive house design and detailing. Next slide. So here's a finished interior shot. One of the other aspects of this job is NLT floor structure. So both the second floor and third floor assemblies are made with NLT, which is just nail laminated timber. It's a type of mass timber. We use this structural system at times in areas where we want to kind of reduce our overall building height. So this allowed us to compact the volume a bit more, which, as we all know, is important. And it also allowed us to meet zoning requirements for the neighborhood for overall height. So we're able to get 3 stories in above grade and maintain our 35-foot height limitation, while still giving us all the access to the daylight and views that we needed. In this picture again, you can start to identify that 9 square grid concept or planning principle that the house lent itself to. I'm standing right now in the kitchen taking this photograph out. On the right, you see kind of a large, grand staircase that it functions as the connector between floors, obviously, but also provides a tall vertical shaft for passive ventilation that is to our benefit here. Thickness of the NLT floor, it is 2x6, so it's 5.5 inches deep for the timber. But then again, similar to the main floor, we also have a service space on top of that, which is a 2x4 service space that again allows us to run plumbing, electrical, and mechanical through that. The building exterior, this is a shot very early winter last year, just a light dusting of snow. Temperature at this point wasn't, it was just in the single digits below 0, so it's still, for our area, quite balmy. You can see it's in an existing neighborhood. The third floor, which on the side to, I guess, the left of the screen, has a large, expansive window overlooking the river, which we're just essentially the house, the low bungalow on the left is the closest to the river. So now we've kind of like afforded some views and some connection to that. Just one last thing I want to touch on is the cladding. It is obviously kind of, quite identifiable on this house. It's recycled metal tile that we've done a few projects with to kind of refine the process and the technique. What it does for us is it gives us a relatively lightweight, really robust, but human scaled and kind of, it is quirky, but it's also identifiable when you can see it, you can feel it, you can interact with it, and it will continue to change over time. The lighter tiles in there are made with zinc, so we're expecting that those light kind of shiny tiles to patina and grow with time, which is something when you're building houses or buildings that we intend to last for the next 100 years. It's kind of just a special thing to try and acknowledge the passage of time.
Next up, we have Rock House from the United States, presented by Stash Zakruzewski of ZH Architects.
Hi, everybody. Good afternoon. Really happy to be presenting here today. I think it's a great idea. A lot of good vibes over here in the city with all of these crazy Norwegians running up and down the street yesterday. It's great. So yeah, I'm here to talk about an interesting project. And I guess the big question for us is, can we build kind of a contemporary glass house with a lot of glass, obviously, in a very forested area? And this one happens to be in Connecticut. It's in the northwest corner of the state. It's in a 38-acre lot of land that our clients bought in 2018, and it's overlooking a very clean river called the West Aspetuck. And it's in a very deep valley. If you want to go to the next slide. So it is in a very deep valley with compromised light and very dense tree canopy in the summer. There's also an interesting history to the site. This was relatively close to New York City and Boston and all these kind of major urban areas. And in the 18th and 19th century, there was a real need for charcoal. So what they would do is clear cut all the land, and they would create these mounds and burn all of the trees. Terrible thing. And they would leave one or two trees so that they could propagate again. But they would cover them with mud and then get all the charcoal to fuel all of these furnaces. So the site is interesting because it has all of these old burial mounds, these areas that are left over from that era. And we refer to this a little bit later in the project. But these are just some views of what we have in terms of the site. So our clients wanted a really great building, one that used low amount of carbon, embodied carbon, and also one that really connected with the site. So next slide, please. So this was the first concept sketch. It's literally just two planes of wood with glazing with the house up in the canopy. And it was doing that for a few reasons. A, so that you could literally bring all of the outside in at that high level. It would avoid all these huge rocks and boulders on this very steep kind of mountainside. And then it would also try and get you some connection to the river there. So that idea kind of developed into the structural concept. You can see here on the right-hand side, the wood building under construction. We had considered using CLT, but it ends up that CLT is very, very fiber intensive. In fact, this hybrid solution uses about 80% less fiber. And it's good to note that because these days it's all about, CLT. And I think we have to consider how to build in these smaller buildings. But we had to do all of the, in terms of passive house requirements, we had to do all of the requirements or all of the calculations to try and figure out how much energy we could glean from the sun in this lowered position with this tree canopy. But luckily, we have deciduous trees, which are very open in the winter. So a lot of energy modeling, and I guess a few things about the envelope. The roof assembly is R86, so a lot of dense packed cellulose between the joists. We have a small amount of polyiso above that, and in the floor deck, R90 of insulation, obviously. So it's very unusual to have a building coming up like that. It was done so that we could go and shift and kind of jump over one of the pathways that was joining one of the old logging roads. So that was important to us that we do that. The other thing that's really important is the motorized shades. They have a lot of impact on the house. There are very, very large cantilevers all the way around the house that really does help adjust and make sure that there aren't too many heat gain times when that sun is high up. There are sometimes later on the day when the sun is higher up and coming into the house a little bit, and sometimes the shades need to be brought down, sometimes not. But overall, the house is performing incredibly well. For an all glass house, I'm sure you've all been in buildings that have all glass. You sometimes get really hot as you get to the glass. This building performs really, really well. It's very comfortable. So we had to do a lot of modeling with other programs other than PHPP, because it's so it has so much glazing, right? We had to do a lot of extra insulation to make up for that glazing, but we also had to do a lot of modeling to make sure that we wouldn't get too hot in certain places. We also have a lot of natural ventilation in this building. So it's designed to bring the air in on the lower floor and then take it out in the upper floor and also in the skylight. The clients, what we did is we designed this mosquito screen on the front terrace, and they open the doors and the windows, and the air just flows through there. So that's really, really important that on the shoulder seasons, this house can perform, without any mechanical ventilation at all. And we're very happy about that, having spent a bit of time designing it for that purpose. It has an ERV. It has all of the functions in all of that area. But one of the things we wanted to do is make sure it could work with natural ventilation. This slide is all about the rainwater management. It is the town had a 20-year rainwater code requirement to manage rain event, and we said to them, look, we don't think 20 years is enough nowadays. You should be thinking of more, and we told them we were going to provide 100 years. But we're really glad we did, because within 2 years of that date of getting approval, we did have a 40-year event. So, and the building was not finished, but it handled it fine. So it has the 2 green roofs. It funnels the water to these different rain gardens. It also has a 10,000 gallon tank that also administers that water in those rain events. So that was also important. I think you can go to the next slide. Yeah, and there's some winter views. You can see how much of the building is actually cantilevered. And this is important because, if you do that, yes, you are using more cellulose insulation, mostly cellulose, in that floor sandwich that's cantilevering out. But if you think about it, there's only about 50% of the whole enclosure of the roof that has concrete basement form. So actually this building has much less than the average building in terms of, concrete, which means higher embodied carbon, etc. The embankments are a gesture towards the form of the landscape that appears and that kind of adjusts into the building, and that's mimicked into the substructure of the floor as well as the roof canopy of the building. So overall, the building is also, it's actually a house and guest house. They wanted two houses and we convinced them to put them all in one. So the guest house program is in the floor below. And we managed to convince them to reduce the floor size from, the building size from about 6,000 square feet down to 3,000, a little over 3,000. So we're happy about that. And overall, the global warming potential analysis shows about a 60% reduction in operational body carbon compared to conventional single-family construction. So thank you very much for your time.
Thank you so much, Stash. Our final small project in game one is the TAPHA Taller Passive House from Mexico, presented by Marisa Ejia from INHAB.
Hi, hello. Thank you for having me here. It's for me an honor to present this project. As you may guess, presenting this in English is a bit of a challenge for me. So I'm going to do it in Spanish on behalf of all the speaking Spanish audience that is joining us today. And because this project was such a challenge in a context that was very new to energy efficiency in the Passive House standard. So in order to make more people to get into it, I'm going to do it in Spanish. So here I am. Next slide, please. Pues muchas gracias a todos por escuchar esta presentación. Para mí es un honor presentar ante ustedes TAPA, Taller Passive House. Es un proyecto bastante particular porque no inició como un encargo profesional, todo lo contrario, fue un taller, un laboratorio que sirvió de experimentación y de aprendizaje para quienes participamos en él. Fue un proyecto, es un departamento situado en la azotea de un edificio en una zona céntrica de la Ciudad de México. Y fue un proyecto plagado de intenciones personales que representó desafíos de todo tipo, de inicio a fin, pero también nos trajo muchos logros. Será un placer para mí presentarlo ante ustedes. No me detendré tanto en la parte técnica, porque todos ustedes están muy familiarizados. No es un contexto, o bueno, en la audiencia de Estados Unidos y Canadá están muy familiarizados con el estándar, pero en México y en otras latitudes es un contexto con un clima muy diferente y aquí los desafíos, he de decir que son otros, al menos los que nosotros vivimos en su momento. Siguiente ponencia, next slide, please. Next one. El departamento tiene orígenes en el 2007, cuando el arquitecto Alejandro Herrera decidió construir para sí mismo un pequeño departamento de 42 metros cuadrados en la azotea de un edificio en la zona central de la Ciudad de México. Tiene estructura de acero, cubierta de concreto, pero la envolvente se hizo con materiales temporales, puesto que contaba con un presupuesto reducido. Y eso le permitió iniciar su vida en pareja, migrando de la zona periférica de la ciudad a una zona central. Sin embargo, a los pocos años, los materiales empezaron a ceder la vida útil, requirieron mantenimiento, requirieron sustitución y además la gran familia que se estaba formando ahí ya estaba padeciendo las inclemencias del tiempo, ya estaba viviendo el disconfort de una ciudad que además de vivir en teoría en un clima templado, sí padece noches frías y sí padece temperaturas muy altas durante mediodía. Así que en 2011, cuando la pareja vivía en Alemania, estaban realizando sus capacitaciones o haciendo sus prácticas profesionales, Alejandro tuvo la oportunidad de participar en distintos despachos de arquitectura, conoció el estándar Passive House allá y habiéndose planteado la rehabilitación de su vivienda en Ciudad de México, decidió generar una propuesta conceptual que introdujo en el primer concurso iberoamericano Passive House, que se llevó a cabo en España, en la tercera conferencia española. Y ese proyecto conceptual resultó seleccionado como proyecto finalista. Así que se llegó a la noción de que era un proyecto certificable. Siguiente, por favor. Next one, please. En el 2012, Alejandro vuelve a México, me invita a participar y es ahí donde empieza otro desafío, el hecho de hacer una propuesta realidad. El primer desafío consistió en capacitarnos en las herramientas de cálculo de balance energético, conocer el PHPP, traducir lo que para en ese entonces era un proyecto conceptual a algo realizable y cómo medirlo. Ese fue el primer desafío. El Instituto Passivhaus, estando sorprendido por la iniciativa de Alejandro en el proyecto que presentó en España, lo impulsó, le apoyó y nos fueron orientando. Surgió toda una fase de autocapacitación, de ser autodidactas, de enterarnos de cómo realizar este proyecto. Y la sorpresa fue cuando se nos otorgó la carta diciendo que este proyecto sería el primero certificado en México y el primero de su tipo en toda Latinoamérica. Se imaginarán que el reto fue impactante, nos llenó de impulso y a partir de ahí inició la primera parte donde teníamos que desarrollar el proyecto con todos los detalles necesarios para que esto fuera una realidad. Encontrar proveedores que supieran y que conocieran los detalles técnicos de sus productos para ser integrados en la calculadora de balance energético fue un primer desafío, porque aunque había materiales para llevar a cabo una edificación eficiente en México, el mercado no conocía las características técnicas, o al menos no estaba familiarizado con lo necesario de ellas para un proyecto de esta índole. Fue necesario entrar a detalle, fue necesario involucrar a personas que participaron activamente y que apoyaron la iniciativa. Y la obra empezó finalmente en 2013 con recursos propios. Insisto, no fue un encargo profesional, pero se pudo llevar a cabo. La siguiente diapositiva, por favor. El reto real fue ejecutarlo, porque en este contexto todos o gran parte de los principios Passive House eran novedosos. La estructura metálica permitió desmontar toda la envolvente y rodear con un material absolutamente nuevo todos los muros, el piso y la cubierta. Conservó la cubierta de concreto, pero se le pudo colocar el aislamiento de 3 pulgadas alrededor de todo el departamento. Eso permitió trabajar y proteger los que en su momento eran puentes térmicos. Así que, además de eso, la incorporación de ventanas eficientes fue uno de los grandes desafíos, porque como mencionaba, el mercado local no estaba familiarizado con las características técnicas que el proyecto requería. Alejandro tuvo a bien localizar a uno de sus colegas, que es otra persona en México que tenía proveeduría de ventanas de alta calidad, y fueron ellos quienes nos apoyaran en gran medida que este proyecto pudiera ser una realidad. Además de ello, la hermeticidad fue otro tema desafiante porque en México no estamos familiarizados con la hermeticidad. Nuestros climas no lo requieren o no lo requerían, al menos en nuestra concepción. Después del proyecto, toda nuestra idea cambió. Y este fue un parteaguas en el entendimiento de la eficiencia energética. Los materiales no estaban disponibles en México. Las cintas y todos los productos para el control de hermeticidad tuvieron que viajar en maletas de Alejandro y su familia de Alemania a México, porque en México no había proveedores locales. Otro desafío fue realizar la prueba de hermeticidad. Tampoco había técnicos que la ejecutaran en México. Así que el instituto nos puso en contacto con un técnico español que acabó haciéndose hermano nuestro por el desafío que implicó y conociendo el reto, puesto que él apoyó la primera certificación en España, eh, empatizó con nosotros y nos apoyó de principio a fin para revisar todo lo que implicaba la hermeticidad, incluso la calibración de los sistemas de ventilación. Que también fue desafiante porque en este clima no hay sistemas de ventilación con recuperación de calor, al menos no hace 12 años. Y eso implicaba importar un equipo para un proyecto pequeño en un clima templado y la costo-eficiencia eh, no era la mejor. Se tenía que invertir mucho dinero en importar equipo de esta envergadura. Y finalmente se le propuso al Instituto Passivhaus un sistema híbrido que era extracción de ventilación con rejillas de inyección. El instituto revisó absolutamente todos los detalles técnicos y nos dijeron que esto era factible. Así que, habiendo alcanzado todo lo necesario, para 2014, la vivienda, el departamento rehabilitado con criterios Passive House ya era una realidad. Para los habitantes representó una mejoría en la calidad de vida. La temperatura interior cambió radicalmente. Ya se contaba con un gran confort acústico en el centro de la Ciudad de México, lleno de bullicio. Ya podían tener noches de descanso, ya tenían gran calidad de aire al interior de la vivienda. Se redujeron las facturas de pago de servicios y se logró lo que en su momento parecía una utopía, la primera certificación Passive House en México, la primera vivienda Passive House en Latinoamérica, y 10 años después, sin que lo hubiéramos buscado, llegó a nosotros la noticia de que el ministro de Eficiencia Energética de la India, junto con otras instancias internacionales, habían seleccionado a TAPA, el taller Passive House, como uno de los 100 edificios icónicos sostenibles por la presidencia del G20 de la India. Para nosotros, esta fue una noticia sorprendente, nos hizo impulsar más nuestro hacer cotidiano y nos hace transmitir a todas las personas interesadas en altos estándares de eficiencia energética que es real, es viable. Se requiere sin duda la participación activa de todas las personas involucradas y afortunadamente al día de hoy el mercado ha cambiado. Los siguientes proyectos en México se los comprobarán. Este fue el primero, fue muy desafiante, pero se logró y satisfechos de haberlo logrado, ahora compartimos con ustedes pues este éxito y junto con todas las demás personas que ahora están ejecutando proyectos Passive House en México. Muchas gracias.
Thank you. We're moving on to game 2 now, our showcase of large projects. And first up, we have Casa Tulum from Mexico, presented by Paul Prida Noriega of Passive Engineering.
Well, my name is Paul Prida. I am a civil engineer, been in construction my whole life, 42 years old. And I decided to build this passive house in Tulum, Mexico. First, I'd like to talk about the decision that took me to do that. It's very different in Mexico. We have a very low construction quality compared to Canada and the USA, Europe, because our standards are very outdated. So the people that come here, it's a tourist area, the Riviera Maya. They don't find, if they want to buy or rent high quality construction, well, they don't find it. They just find the existing quality construction. So I decided to attack that niche, try to bring the best of standard constructions here to the Riviera Maya. The market, I'm betting that the market would like that, especially the people that come from markets that they have a higher construction. And the situation is changing in the world. Before, the cost, it was more difficult. The people are more focused on the cost of building with higher standards here in Mexico. But with time, as the same as happening in Canada and the United States, the labor cost is going higher. And as the labor cost goes higher, well, it makes more sense to spend more on high quality materials and invest in higher quality standard. So one of the things I'm trying to do with this house is elevate the standard of building in Mexico. Next slide, please. Well, we started with the concept. These are some of the renderings. We are in a golf club. It's a PGA certified golf course here in Tulum. It's called Tulum Country Club. And we use a lot of natural materials. This is called chucum, the material that you see on the facade. it comes from a tree, but now it's becoming more industrialized. Difficult to describe, but it's like a plaster, very nice one it feels. We also have wood, the Mayan rock. It's called, that's what we call it, the Mayan rock. Can we go to the next one, please? Okay, it's not working there because I had some pictures over there. I cannot see them here. Okay. In the slide before, doesn't matter. No, go to the last one. There, I had some floor plans there. I can send them to you later because it's not showing there. But as a civil engineer, architecture is not my main strength. So I try to make this house as easy as possible to certify. So it's a rectangle, as you can see here, and it has as little windows as possible. Ignacio Fourniers, he's my PHPP designer. He's also in this conference. Before we started to build, we started modeling with the PHPP, and we put more shade. We have a big terrace in the back, as you could see in the first slide. It's a big chukum terrace, a palapa, we call it here in Mexico. It covers the biggest window, which is the greatest architectural feature of this house, but we give it a lot of shade with that. We also consider the space in the walls. Mexico, normally the walls is just block, we call it brick. That's it. We have no insulation required by the government. So walls normally are 4 to 6 inches thick. So it's rare to have 12-inch thick walls to fit the insulation. We had to pick the insulation materials. We don't have a lot of materials as you do in other countries, but here we had expanded polyester, and we compared it to other ones that we have, the extruded polyester and rock wool. We chose expanded polyester because of cost and because it gave us the necessary insulation. So that was very interesting. We didn't have a lot of problems getting it in Mexico because it's very normal. This material, fairly easy to get, but it's normally used for the slabs, not for insulation. But fortunately, we could get it. I also put a picture there on the roof. We had triple insulation. We have 12 inches in the roof, and then the rest of the walls and the foundation, we have only 4 inches. Please, the next one. Okay, so the mechanical ventilation, I think this one was the single greatest challenge here in Mexico because it was impossible to get the mechanical ventilator, the recuperador de calor, we say in Spanish, because we didn't have certified equipment here in Mexico. So I had to import it from Spain. This is the equipment in the lower right corner. It's a Sender Q450. Because if I didn't import them from Spain, we would be forced to certify the new equipment by Passivhaus. So we chose this time not to do it in order to make it easier for the certification. Also, the airtight material, you can see it in the middle lower photo. It's Rotoblas, it's imported from Italy. Fortunately, we did not have to import that because Rotoblas is already established in Mexico and they imported it from us. So not all the materials had to be imported. An issue that popped in the middle of the project is that it was not enough with the mechanical ventilation. We needed a dehumidifier. I pointed out in the top left. And the challenge there was that we needed cold water. So we needed to start a chiller. It's in the top right, to provide cold water to the dehumidifier and the air conditioning. And it was hard because none of this is done in the residential building here in Mexico, but I'm very happy I did it. I want to do it again. Next time, it would be easier now that we've done it. This house is going to be certified in the next months. We are right now 90%. Please, on the next one. Some photos of the windows. Also, the air tightness was with the same company, with Rotoplas. And windows, we have a lack of technical people that can put the windows. The market here is dominated by Kommerling and German companies that make the PVC profiles for the windows. And the problem is that they're very expensive. I'm hoping in the future it would change because it's just dominated by German companies. And in Europe, I know that the PVC windows are cheaper than the aluminum windows. I'm hoping that can change with the future. A new company called Salamander is the one that fabricates. It's also from Germany. It's a 100-year-old company. Made these wooden, well, PVC windows, but with wooden finish. And this is the biggest window, and you can see the palapa outside that gives it shade. Next one, please. Well, I cannot show you. I had a technical specification here for the window and the blower door equipment. The blower door equipment, let me tell you what is here it is. The blower door equipment, it's a very big challenge here. I tried to hire it, but it was in the order of $8,000 for the test. Didn't make sense. So I decided to buy the equipment myself. It cost me $5,000. I imported it from Minnesota. I now have it here. So anyone that wants to do blower door test in Mexico, I can now help them, and it would be easier for everyone else. I'm happy for that too, because there's no blower door test here.
Thank you, Paul. Next up, we have Harmony Commons at the University of Toronto, Scarborough from Canada. This is presented by Irvin San Juan of Pomerleau Construction.
Hi, good afternoon, everybody. Irvin, I work for Pomerleau as a project manager. We're a Canadian general contractor, and today I'm going to be giving you a presentation more from the general contractor side, so more from the builder side and the challenges that we had with this particular project. So what you're seeing there is a client of ours. So this is a residence building for the University of Toronto called Harmony Commons. It houses, it's got 750 beds. So essentially 750 students reside here along with the university staff. So we can just get the next slide, please. So this is just a little bit about Pomerleau. We're a $4 billion company, and we were founded 60 years ago, and we're one of Canada's top 100 employers. Just a little bit of introduction on Pomerleau. Next slide, please. And this is something about the project. So as I mentioned, it's 750, or in this case, 746 dormitory style beds, 9 floors. It's got many amenities within the building, within the space. It's got a terrace, cafeteria, administrative offices, storage, and was Passivhaus certified in September of 2023. So at the time when this building was certified, It was the largest of its kind. I'm not sure what the largest is now, but at the time that we did get certified in September of 2023, this was the largest passive house project, and being the largest, of course, building to the scale and to the like newness of Passive House at the time, we did encounter a lot of challenges. May be a lot to discuss over a 7 minute presentation, but I'll try to kind of rip through whatever challenges we had for this project. The facade in general is made of a metal cladding, so a lot of thermal conductivity that we had to deal with. There's a lot of window openings. I heard Paul mention earlier that the house that he designed, he tried to eliminate as much windows as possible. This project in particular has over 800 windows, and they are all operable. So it's actually a bit of an enemy of the passive house. So we had a hard time basically making sure that everything is installed with quality, and we were able to maintain that air tightness in order to pass the air changes per hour that we would be tested on later on into the project for the certification. In terms of material logistics, we had a lot of challenges because this project was being built during COVID time, and as again Paul mentioned earlier, a lot of these materials really come from Europe. So the bottom windows there that you see at the ground level, those are curtain wall units. Those are sourced from Germany by Schueco. And the punch windows that you see all around the building is sourced from Colorado from a company called Alpen. Next slide, please. Some of the project successes that we obviously had here is achieving a lower and a better target than what we had planned for and what we had designed for. So our target was 0.6 air changes per hour. After all is said and done, and after all the tweaks that we had to make for a scale of this project, we were able to achieve 0.4 air changes per hour, and most importantly, we were able to deliver housing for 750 students for Toronto, for the University of Toronto, which was amazing. They're an amazing client. Next slide, please. So yeah, the building had a lot of interesting design elements to it. One in particular is the mechanical system, which was designed to basically recuperate heat energy by having a duct-in-duct system. I'll show you a photo on the next slide, but basically it recovers heat loss from a kitchen exhaust and recirculates that heating that would have been lost, that would have been exhausted to the exterior, back into the interior during the winter time. So obviously this would be very useful in achieving our energy targets. But yeah, that's the general idea behind the duct-in-duct system.
Thank you so much, Irvin. Our next large project is NYU's Rubin Hall from the United States, presented by Cheryl Saldana from Simpson, Gumpertz, and Hagar.
Thanks, Jessica, and glad to be here with you all today. Hola, bonjour, good day for all of the multilingual folks out there. This will be in English. So first off, I want to sort of introduce our World Cup squad here. I may be speaking, but this project was a success because of the dedication of everybody that you see on this team. Couldn't have done it without everyone here. Some quick stats about the project. So NYU Rubin Hall is an existing building located in the historic Greenwich Village district in Lower Manhattan. So the exterior is landmarked, and it was originally built as a hotel back in 1926. It's 16 stories, mass masonry. It does have a rooftop penthouse structure that's not visible in the photos. It's set back from the facade. NYU, New York University, took over the building in the 1960s and converted it into a student residence, which it's has been that till today. When we were introduced to the project, it had no air conditioning. Oil-fired steam boilers was how they heated the building, and a lot of, student comfort issues again because of the no air conditioning. NYU is super committed to becoming a climate neutral campus, and so this project was selected to be a deep energy retrofit. And so there's a strong focus, even from the beginning of the project, to enhance student well-being through better indoor air quality. There's a need to implement all-electric systems as part of the retrofit to meet some of the New York City local laws that are coming up. And that needed to be coupled with comprehensive envelope upgrades because we don't have much rooftop space to fit all these electric equipment systems. And so here's where the Passivhaus and specifically the EnerFit framework really served this project well. And we actually used the phase implementation where we renovated basically the 15 stories, and then the top penthouse level is being done as part of a phase 2 retrofit. So if you can go to the next slide, let's start with kind of looking at the existing conditions. So you can kind of see here, we have uninsulated masonry walls. In some locations, multiple layers of brick. In other areas, we have hollow terracotta with interior plaster. The windows, if you click, it should pop up. The windows are steel framed, non-thermally broken, single pane glass. So pretty poor thermally performing and very drafty. And then we ran this pre-construction blower door test, and we measured 6 air changes per hour. So this building is breathing heavier than a midfielder during stoppage time. The other thing about this test is it showed us where we needed to focus, right? We knew we had the window leaks, but now we also identified air leaks through things like rooftop shaftways, and at the cellar level, we have these sidewalk vaults and light wells that are also sort of connected to the building. So yeah, let's get into the envelope systems. Air barrier here. So, first we thought we could use the existing plaster to be our air barrier, right? If plaster is well installed and continuous, it's going to be a great air barrier. In our case, though, this plaster was original to the building. It's original horsehair reinforced plaster in some areas, and it had become unadhered from the backup walls in some locations. So from the contractor standpoint, if they start to try and patch these areas, it really quickly just unzips and comes off, and it would be actually a real risk to the schedule of the project. We had a very tight schedule of 14 months when the building would be empty, so we had to get this all done. So rather than trying to repair all this plaster, what we ended up doing was adding a layer of 1/4-inch thick fiberglass faced gypsum board, fastened it directly through that plaster, created that continuous air barrier, taped all the joints and seams and penetrations, and then in that left-hand photo with the dashed red line, you can see the air barrier actually jogs around every dorm unit. So every student unit is a self-contained box. In the middle here, you can see our insulation strategy. So here, because we have this existing masonry building, we lab tested. We took brick samples, lab tested them, performed hygrothermal modeling to determine the ideal thickness and type of insulation, and we landed on open cell spray foam with an interior variable permeance vapor retarder directly behind it, and that membrane is also again taped continuously to all those penetrations like sprinkler heads and electrical boxes and plumbing and light fixtures. And really the idea here is we need to add insulation, but we still need to let the walls breathe. Don't want to trap moisture or condensation in there. And then third on the right is the windows, so triple glazed, tilt and turn units with offset glazing because we need to replicate the historic look of a double hung window. These windows are much deeper, heavier than the original steel framed windows. So while they are sitting on the masonry opening for gravity loads, we had to figure out the lateral attachments. We couldn't just fasten directly to that hollow terracotta. And again, thinking about the schedule of the project and trying to keep things moving forward, worried about, blowing out some of that terracotta and having to make repairs or trying to grout fill the cells and allowing that to cure. So what we ended up doing was having these lateral supports. You can see in the photo, those plates that brace the windows laterally off of interior stud framing system. That meant our waterproofing, flashing, air sealing details had to work all around those plates. And there was a lot of coordination we had with the contractor teams to work through the sequence of the installation between the insulation installer, the waterproofer, the window installer, etc. Now onto the mechanical systems here. You can see, so from a mechanical standpoint, I mentioned we permanently benched our oil-fired boiler and switched to these all-electric systems. For fresh air, we have, ERVs on the rooftop, pushing that ventilation air through existing shafts in the building. So we were lucky that we had these shafts to work with. And then recovered heat from bathroom exhaust. For heating and cooling systems, we have air-to-water heat pumps that feed the water loop to fan coil units that are in each room. So there's fan coils below the windows. And then for hot water, separate set of electric heat pumps to serve that system. The theme across this is the same. We're electrifying everything, recovering heat and energy where we can, and reusing the existing building infrastructure as much as we could without tearing it down. So did it all work? Well, here's the final score. So our blower door test went from that 6 air changes per hour down to less than 1. That's an 85% reduction in leakage. Our operational carbon dropped by roughly 45%. Energy use intensity by 55%. The building now avoids local law 97. In New York City, we have this local law. It avoids those fines through at least 2034, so no relegation for us. And the project was supported by NYSERDA and Con Ed, which helped with the economics for sure. And if you just click again, I just want to share as I wrap up here, my favorite story from this project is, if you remember, this last winter was a pretty cold one. In New York, actually, we hit some record lows for temperatures. This is in Fahrenheit, by the way. And the fan coil units actually went down for a week during this cold snap. So if you look again, for an entire week, we had no fan coil units and we got no complaints. So this building was able to hold its temperature on its own. And to me, you can show people all these numbers on the left side, but at the end of the day, the real payoff here is when you get the envelope right, you can get, comfort, resilience, and really big carbon savings. So thank you so much. Gracias, merci. That's Rubin Hall in a nutshell.
Thank you so much, Cheryl. I believe that's about 0 degrees Celsius. Our final game is the commercial projects, and our first project up is the Texas Pickle Hall from the United States, presented by David Comet of Urban Earth Advisory.
Excellent. Thank you, everybody, for allowing me to present. I'm excited to be one of the contestants. And in response to Fletcher, I did go up, dig out my appropriate gear, even though I won't put it on. So I'm flying for the flag. So the Texas Pickle Hall is it's not a pickleball facility. It's an active entertainment venue. It's really more of an active lifestyle social club. And the Passivhaus method was always part of the business strategy and part of the development program. Urban Earth is my business. We are a consulting firm. I'm not an architect and I'm not an engineer. I really come from the investment development space. So my comments today are going to focus on A, what a great place it is, but B, what was the business case for why we brought Passivhaus to this project. So the Texas Pickle Hall is about a 32,000 square foot large volume building. This is my first Passivhaus project. I figured this would be an easy one to do. I was wrong. I didn't realize how complex it can be to unlock some of the commercial building sheets in the PHPP. We are in a hot and humid climate zone here. This is climate zone 2A, and so we're always very concerned about humidity. And the question we had to answer was, how do we take a high occupancy, high variable occupancy building in a hot and sweaty climate with a bunch of hot and sweaty people running around hitting a ball? And how do we achieve comfort and durability in the building, as well as drive down our energy costs? So my answer to this was, I used the Passivhaus method as a development tool, not really as an energy standard, not really looking at decarbonization or anything else, really looking at how do we deploy this as a development tool? How do we value engineer the building? And we were very successful in doing that. You can see, I'm going to get into it a little bit later, but our big issues in this climate zone really revolve around the mechanical equipment. Anybody who's managed a building in a hot, humid climate, certainly my friends in Mexico can relate to this. You're going to be dealing with humidity primarily. So these are the envelope of verification that we achieved. We killed it on the ACH 50 blower door test. That's a function of me literally following all the contractors around the site with my little ultrasonic testing equipment and talking about caulking and taping everywhere we could. They did a great job on that. Where that really plays out in the PHPP is we had 0% on our humidity exceedance. There's an allowance for that for our climate zone. I was very happy about that. Our cooling load was below the allowance in the PHPP, and we really have virtually no heating load. The primary heating loads on this building are internal heat gains, 68% from the lights on the courts and the balance from the people playing there. So there's further opportunity for us to value engineer this more through the lighting systems to drive down our internal heat gains. Let's see. Yeah, so I mentioned hot, humid climates. Look, our big problem here is people tend to deal with our loads by oversizing the mechanical equipment. We were not alone. We received a standard code compliant design in the beginning, and I'll touch on that in a minute, with about 88 tons of mechanical cooling specified. So what we do now is we decouple our heating and cooling from our dehumidification, from our fresh air ventilation. So we really focus on decoupling that. The engineering on this building, this is the first project I've done like this, yielded an integrated system, which is very elegant, surprised me, and is a little bit complicated to control, but we're getting our hands on that. And I should say, para mis amigos mexicanos, todo la envolvente y la estructura del edificio se fabricaron en Mexico. This entire building was fabricated in Mexico and brought into San Antonio. So it is truly an international project, and we're thrilled to have it as part of the international competition. The strategy for that mechanical, can you go back to one slide real quick? Mechanical strategy, we have a Swagon giant ERV wheel. If any of you have dealt with the RX-50 units, I wasn't prepared for when it landed. It's very simple to work, but very sophisticated, very impressive. We move it then to a connected Daikin DX coil where we're overcooling and wringing out some of the moisture. And then we've got this cool post-heat coil, which I had never used in a project before, where then we reheat the air to bring it back to the temperature we want to deliver it at. And that post-heat coil consumes no additional energy. It uses waste heat from the Daikin DX coil. Can you go to the next one? So this is the big idea on this project. What were we able to achieve from the business side of using Passivhaus? I'm in San Antonio, Texas. When I talk about Passivhaus, I always lead with the health of your family, the health of your children, and how your building's just going to be more durable, more valuable, and you're going to end up with a much better piece of real estate. That's how I talk about Passivhaus in my market. So you can see we're able to drop our capacity for the cooling equipment by a little over 70%. We had this ugly collection of 7 packaged units surrounding this building with the appropriate ducting going up the side. All of that went away. We have a nice clustered three unit situation tucked away in a corner of the building. Very compact and very, actually looks kind of nice. Our electrical service, we were able to cut in half from 400 amps down to 200 amps. We were able to eliminate all of the copper wrapping around the building with these 480 volt lines. All of that went away. We were able to reduce our electrical demand. We dropped it from 286 kilowatts to 45. And we're using, again, the Swagon mechanical ventilation is really the unsung hero, or just the ERV in general. is the unsung hero of this project, and certainly one doing this project that stood out for me. That's really a focus that all of us in climate zones like this need to address. It's all about the ventilation. And so we're very successful in achieving that. We actually don't sell pickleball. We don't sell birthday parties. We sell fresh air. And for all of us who've been in certified passive house buildings, we know what that means. And as I said in New Haven, my favorite line now is once you breathe it, you can't forget it. It's just once you experience that crisp, fresh air experience of being in one of these buildings. So from my perspective, our payback is not over time. Our payback was right on the front end. We immediately are dropping first dollar CapEx cost on this project. And so by just slashing 88 tons to 26 tons, you can figure out about how much that was. It was significant. And in my view, we're recouping that on day one with the ongoing stacking effects of lower OpEx and lower replacement costs. So there was zero premium to us on CapEx delivering this building. We delivered it actually a little below market on cost. We've got dramatic energy savings going forward, which is a business story for us. It makes the operation more viable. It also makes our building worth more money. We have lower expenses on the building, which increases our net operating income. Apply that to a market cap, and by my calculations, we added $1.5 million in additional value to the building. And then dropping our electrical, infrastructure, was a big win for us. So all in all, we use Passive House as a business strategy to value engineer it. It's a big box. We think it's more attractive than the standard metal building everyone was looking for us to deliver. And again, as time goes on, I hear more and more from our constituents, from our members, people that have events here, how good it feels to be in the building. That's the comment, how good it feels to be in there. And so that's our conversation in our community is, well, how does it feel at the other place? How does it feel in your home? Because it's exceptional. And we're gathering data on this, and I hope to share that, a year from now, or maybe at the International Passive House Conference, to show exactly what's going on inside of this building around humidity, PM 2.5, and CO2 levels.
Thank you so much, David. Our second commercial project is the Eco Casa Passive Lisboa from Mexico, presented by Elena Reyes Bernal from Passive House Institute.
Thank you, Jessica. So it's a pleasure to be here. I would like to start by saying that even though we still have people pioneering high energy efficiency buildings in Mexico, like Paul and Marisa, the discussion about energy efficiency it's relatively old. Like the Passive House Institute has been working with different institutions in Mexico to try to further develop high energy efficiency since 2011, being it studies, feasibility studies, development of tools which work with PHP in the background, and pilot projects. Next slide, please. So this project, the Eco Casa in Nogales, is actually the result of one of these projects where we were able to build some pilots. At the end of the day, we worked with several housing developers. With 4 of them were the ones that managed to build different pilots, and that we were lucky to be able to do that in several climates. Next one. Lisboa, the Eco Casa Pasiva in Lisboa is located in the north of Mexico, so the climate is very hot and dry. These projects were all social housing, which means that the price has a very, very low cap. So we had to make sure that even with the additional investment costs, the price wouldn't be so high that it wouldn't be affordable. The project had funding from the German Development Bank, so we were able to have training of the design teams, the energy consultants. For example, Marisa was part of this project as well, and then we also had a portion of the energy efficiency measures being financed by this funding, but still the projects had to be kept within a budget. So these are very tiny houses. This prototype was 60 square meters. That's 660 square foot. And inside this teeny tiny house, they packed in 3 bedrooms, 2.5 bathrooms, and a teeny tiny kitchen with a living room and a dining space. So now, can you go back to the other one, please? So we knew from the beginning what Paul and Marisa already hinted at. We knew that we would be able to get probably insulation, but things like mechanical ventilation and air tightness are not concepts that are implemented in construction in Mexico because there's no regulation asking you to do that, right? So we had to find a way to to see which products we could get and then find solutions in a way that they would be able to construct these prototypes within the planned schedule, within the framework of the program, and still be able to achieve passive house. So in this case, for example, even though it's a very hot, it can get very hot, the easiest solution here was to do without a ventilation unit with heat recovery, and we actually only had a very simple system with extract fans in the bathrooms and the kitchen, and then direct supply vents into the living room, and each one of the bedrooms. But what we had then to do is to compensate that with additional insulation and much better windows. So we have here what we refer to as expected reductions. As part of the objectives of the program, we had to achieve at least 70% reduction in CO2 emissions. That was the main motivation for the Mexican government for this program. So in this case, we knew that compared to the same prototype without any energy efficiency measures, the savings in terms of energy demand would be 81%, and that translated to 82% in CO2 emissions. The next slide, please. So we were also working with existing prototypes from these housing developers, right? So it is, as Paul mentioned, they also look very much like a box with two levels, and the most common materials they use to construct are concrete. So all the slabs were concrete, and then the walls were made out of brickwork. They already used insulation, but they had never done it to the level that we require to achieve passive house. But that sort of chain was already there, so we just needed to sort out some of the details, and then once we were able to get the windows that they required, we use certified windows in this case. Then the focus was on airtightness. Again, no airtightness products were available at the time. So the main solution for the walls was the mortar from the inside of the walls, and then the concrete slabs themselves are airtight already. So after that, we only had to have a solution for the connections between the walls and the windows, or the doors and the windows, and then the electrical and the hot water penetrations for the houses. So we tried to make it as simple as possible, so that also, as Paul mentioned and Marisa mentioned, the air tightness products that we needed were as little as possible, because these needed to be imported. Next slide, please. So another very important part of this was the work that Marisa and other energy assessors did together with the design teams, right? Like the most successful prototypes were those in which they also trained the construction team, so they were aware of what they had to do, what were the solutions for tightness, or these new things that they had to implement in these prototypes, so that they would achieve the passive house standard. And then, thanks to that combination of very active design teams and local advisors, and the training and continuity of the personnel on site, that we had this successful project. This one did achieve the 0.55 for the airtightness. The next slide, please. I think there's like an animation, but you can click until we see all the information. I just wanted to show you a comparison with another prototype that we did in this program, which was in a very different climate. The one on the left is a very temperate climate, so the level of insulation that we needed was very small. They did away, I think, in this case, also with single glazing. Like in Nogales, we required certified passive house windows, triple glazing, solar control, but the other one was the climate is so mild that in this case, we tried it with single glazing and just PVC windows. You can keep clicking if you want. There's more boxes also on the right. Yeah, you can, one more, perfect. So you can see here the comparison of what we needed. And at the end of the day, we were also able to use very simple systems also for heating and cooling. We just had like a mini split unit for each one of the houses that would provide this. So these were very simple examples, but we wanted to highlight with built projects that it is possible to do passive house, even with social housing and with a limited budget and in very different climates throughout Mexico. The next one, I think this is the last one, so I just want to say thank you for your attention. If you don't know, this year we're celebrating the 35th anniversary or 35th anniversary of Passivhaus and the 30 years of the Passivhaus Institute. So now, for me, it's great to see all these different projects that are happening everywhere in the world, and all of these are also part of the celebration of Passivhaus being 35 years old.
Clayton Community Center from Canada, presented by Elise Woston from HCMA.
So I have the pleasure to present the Clayton Community Center. So it's located in a rapidly growing neighborhood in Surrey, BC. The project was completed in June 2020 and combines 3 community services. There is recreation space, a library, and an arts program. So the program includes a gymnasium, fitness center, branch library, music studios, visual and art studios, multipurpose rooms, community kitchen, a woodworking workshop, and childcare spaces. So lots of things combined into one program. Obviously, it is certified. It was certified Passivhaus, and it's also certified Rick Hansen Foundation Accessibility Gold certification. If you click one more, then you also see here some of the results of the final PHPP, or if you can go back, thank you, where you can see the final PHPP results. So we were pretty, meeting the Passivhaus criteria with quite a bit of buffer. And you can see the airtightness there. The team was really proud to achieve 0.18 HTH at 50 Pascal. Click to the next slide, please. So the design concept for this project was really to create, to make the center as an extension of the forest on the site, and draws on this quality to inspire the design elements. So the roof and the building envelope mimics the tree canopy to unify those kind of 3 program components, 3 services underneath. With a heavy timber structure that spans across the interior. You can see a shot there. So really the concept was to create a strong geometry on a very natural site. Next slide. So really from the get-go, and working with the PHPP early on, we knew that cooling was our biggest challenge. Like hitting the cooling demand criteria for Passivhaus was the biggest challenge, mainly because of the amount of internal heat gain that that project was consisting of, right? And so very early on, the team looked at each element of the program, considered whether views or solar heat gains were desired or not desired, whether internal heat gains were high or low in those spaces. And this directly informed the orientation of each piece of the program. So if I take an example here, the fitness top left corner there, you can see that view were desirable, but solar heat gain not so much. And we have a lot of people, a lot of equipment in that space. And so there was a decision to move the fitness area to the north of the building, as opposed to the library where, actually it's not on this graph. What would be another example, a good example? The common spaces had more of a desire for more solar heat gain and views, and had less internal heat gain, so was moved to the south of the building. Next slide. So another shot. So this is the south elevation of the building, and a few features that I want to point out. If you can click the next slide, please. Thank you. So some of the details of the construction, fairly standard construction for the area for BC. So, steel stud wall assembly with exterior insulation. We had about 150 millimeter exterior mineral wool insulation on the walls. It's not much. And again, it's because we had actually more of a internal heat gain issue, and lowering the amount of insulation was allowing us to reduce the cooling demands of the building. The roof had more insulation. The building is very flat, so the insulation on the roof had a big impact, with 300 millimeter of rigid insulation on the roof. RICO Passivhaus certified curtain wall systems with triple glazing. You can see the pop-ups on the roof. We'll come back to that in a sec, which really helped on the natural ventilation. And we had also sunshades elements, which you will see on better in the next photos. I also want to point out that the window to wall ratio, the amount of glazing limited. Certainly, like you can see here at the top, we had about 38% window to wall ratio on the south, much less, of course, on the north elevation. And I think the east and west were somewhere in between. So fairly low glazing amount, but still we were trying to get the views from the greeneries that you would see if you were to take the photo in the other direction. Next slide, please. So again, we had a cooling issue, and we actually could not meet the Passivhaus criteria for a very long time in the design. And really, the key lever that made us be able to certify it was to introduce natural ventilation. And so if you click on the next slide, so we have implemented automated operable windows. So they were tied to, so the windows would open at night when free cooling was available. And another interesting aspect is that the thermostats are connected. And so if the conditions are favorable for natural ventilation, we have those coded colors on the thermostat showing, okay, it's red, maybe not the best time to open your windows, or it's green, go ahead, please open your window. You're going to benefit from that. But I do want to point out that the mechanical system was, mechanical ventilation was fully sized to work on its own. We do have a lot of smoke from wildfires in the summers. And so we are able to shut off the windows, and rely fully on the mechanical systems. A few of the internal features. So you can see here that roof structure made of glulam beams. The heating and cooling fans were an air source heat pumps, but the distribution system was interesting. It was some radiant ceiling panels that were nested within those glulam beams. The fitness space also included a few ceiling fans. Again, it's not really helping on the Passivhaus front, but certainly on the comfort side of things in the fitness. And for the ventilation side, we had also Swecon HRVs units. And next slide. And just finishing off with some photos here of the interiors. On the left, you have the library space. So south-oriented with certainly more glazing than other spaces. And then on the right, you have the main atrium space or lobby space with the social stair.
Thank you, Elise. And a huge thank you to all of our presenters today. Those are fantastic projects, and it was really fun to hear about projects outside of our own countries. So.